Hello everyone, welcome to chapter 3 and third lecture, that is hydrostatic forces on the surfaces. Okay, so in your fluid statics or hydrostatics, like we study your stress generated in the fluid system. Like stress is your force which is generated on any surface is determined when your fluid is at rest or static condition. Okay, and the total force which will be acting on the surface will be your total hydrostatic force. And we can assume that this total force will be acting at a point. Okay, and that point at which the total hydrostatic force will be acting in the of course in the normal direction I am talking about, is your center of pressure. Okay, so to study this, we like let me start with your total hydraulic force on the plane surface. Okay, we will see some derivations and more things here. Okay, so if I talk about hydrostatic force on surfaces, so for that, for like if we consider a surface, let's say this is a plate and this plate is standing on a ground, let's say. Okay, and on one side there is a water. Okay, so now if I talk about your pressure distribution, so pressure distribution on this plate can be shown as like this. So this is your P is equal to 0, then your pressure will increase in depth. Okay, and this final pressure at the bottom, P is equal to rho g h, if your was the height of your free surface from the base. Okay, okay, so P is equal to rho gh is the pressure at the bottom. Now from here we can say that this pressure is not continuous, pressure is varying. Okay, and hence your hydrostatic force which will be acting on the surface will be like overall will be distributed over the surface. Okay, we know that force is equal to pressure into area. We know that for a small component of force we can write it as your P times of dA. Okay, and since the pressure is varying, your force acting on the wall will also be varying. Okay, so to proceed with that, let's proceed with your first type of plane. Let's consider a horizontal plane surface. Okay, hydrostatic force on horizontal plane surface. So let me mention first point here. Hydrostatic force on horizontal plane surface. Horizontal plane surface. Plane surface. Okay, so if I talk about hydrostatic force on this plane surface, so let's first, before that, let's consider a body. Let's say that this is a free surface of your water. Okay, and at a distance or at a depth h from this, at a depth h, uh, from the free surface of the water body, we are considering a, let's say, flat plate. Okay, let's like reduce the depth of the, this is height h. Okay, here we will consider thus this plate. Okay, let's say your plate is on this level. Okay, and to draw the plate, let me draw it like this. Okay, something like this. Okay. So this is your horizontal plane surface. Okay. So here what will happen, since your like every point on surface, every point on surface is at same depth, is at same depth. Okay. So pressure, I can write that pressure at any point is equal to, pressure at any point will be equal to your rho gh, rho g h. Okay. Or you can also write it as uh, specific wide times your h. Okay, that is gamma h. And we can write that total force is equal to p, pressure into area, will be equal to rho g h a is equal to gamma h. Or let's stop at it only. Okay. Okay. And this direction of force, since like every pressure on this plate will be acting in downward direction. So direction of the force, if we talk about, then that will be also in your vertical downward direction. Okay. Also in vertical downward direction. Okay. Like this, and will be normal to the plane, will be normal to the plane. Okay. This is your F, force F. Okay. And this force will act on the centroid of the plate. Okay. And this centroid here will be your center of pressure. Okay. Now let's talk about your second case, or second state, that is hydrostatic force on vertical vertical plane plane surface. Okay. So if we talk about vertical plane surface, so let's again consider the example. Let's say that this is your free surface of the liquid. Okay. So inside the liquid, let's say this is your some arbitrary shape is there, or this is some arbitrary shape, let's say. Okay. And on this shape we have to calculate what is your hydrostatic force acting. Okay. So here, of course, there are certain things. Let me mention them here first. So let's say this is on this line, at this point is your CG. Okay. CG. Okay. And this CG is at a distance of h bar, let's say h bar. This is the, this gap is h bar. H bar. Okay. Now let's say that at a distance, let's at a distance y from the free surface, let's consider an element. Okay. Having your thickness of dy and width b. Okay. And of course, on the same line, as I mentioned earlier, that your pressure varies from top of the liquid to the bottom of the liquid. Okay. So higher the lower we are inside the liquid, higher will the pressure. Okay. So your center of pressure, which I mentioned earlier, that is a total application of like your total hydrostatic force that should be acting. would be your generally is below your CG. Okay, so this point will indicate your CP, center of pressure, and I will derive it also in your next part, or in this part also we can see why does it lie below your CG. Okay, and this distance is your this distance up to CP is represented by your YP. Okay, center of pressure point, application of center of pressure, and at this point CP is your total hydrostatic force F. Okay, I hope you get till here. Okay, now if I talk about the small your pressure at this point, pressure at the element, so pressure is equal to rho g times of y. Okay, at this point your pressure will be this, and if I talk about the small elemental force df, that will be equal to p times of dA, and dA is equal to, that is your p is equal to rho gy into your a is bdy. Okay, now if I want to calculate your total force, so I have to integrate this. Okay, so F, I can obtain it by integrating your df. Okay, and if I do this, so I will obtain from here, that is rho g integration of by dy. Okay, now this term dy, this term here is basically your first moment of area, is your first moment of area. Okay, and we can also write it as F is equal to rho g a h bar. Okay, okay, because ah bar is also your first moment of area. I hope you get this. Okay, where a is the area of this surface and h bar is the distance of CG, center of gravity, from the top surface. So this is your hydrostatic force acting on this surface. Okay, and this is your total. Okay, like summation of all the elemental oils, since we have integrated it. So this is your total hydrostatic force acting on the plane surface. Now if I talk about the location yp, so to calculate yp, what we can do, we can take your moment. Let's say that this your top is, let's say this is your OO line. Okay, so taking taking moment of for about OO axis, OO axis, what we will get from here, so your dm will be given by your df times of y. Okay, and I can write it as rho g times of b times of y square dy. Okay, and if I integrate this, so I will obtain it as your like integration of df into y, or like if I integrate this, so I will get moment m is equal to integration of dfy will be equal to rho g times of integration of b y square dA. Now this term here, that is your b y square dA, is basically second moment of area. Oh, area, and is also called as moment of inertia. Okay, also your moment of inertia. Oh, okay, and this is represented by I node, I node. Okay, so like total moment I can also calculate by like multiplying this F with Yp. Okay, this is your total hydrostatic force that is acting on the body and is acting at a distance of Yp. Okay, so F into Yp is equal to your rho g times of your I node. Okay, and I node is your moment of inertia about this free surface of the body. Okay, so from here uh, so from here I can obtain my value of Yp is equal to like F is equal to rho g ah bar if I substitute here. So I will obtain Ip is equal to upon I node upon ah bar. Okay, okay. Now if we use parallel axis theorem here, so from parallel axis theorem, axis from parallel axis theorem, what we will obtain? We can obtain your what is parallel axis theorem? That moment of inertia about any point or any axis is equal to moment of inertia across your centroid, that is g, Ig, plus area times of distance between the axis. Okay, chi square. Okay, so now here h bar. Okay, so this is your h bar. Okay, because like distance between cg and this top bar is your h bar here, as I mentioned earlier. So if I substitute I node value here in your Yp equation, so I will obtain my Yp, that is your center of pressure uh, location, or somewhere sometimes it is also mentioned as your Y star, is equal to your h bar. Like if I substitute your ah bar square here, so h bar is divided by ah bar is equal to h bar plus Ig divided by ah bar. Okay, so from here what we see, we can say that since Ig upon h bar is your like all terms are positive here, is greater than 0. What does it implies? It implies that Yp is greater than your h bar. Okay, and it implies that your Cp lies below lies below Cg. Okay, I hope you get this. Okay, so from here we can prove that your center pressure always lies below below your center of gravity line point. Okay, and consider a case where your h bar value becomes your infinite. Okay, it means that your plate is immersed infinitely deep inside the fluid. Okay, in such cases what would happen? In such cases what would happen, like your Ig is your moment of inertia about your central axis, that will remain same, area of plate will remain same. But see, if your h bar is your is inside very large depth inside the water, let's say it in infinite distance, so at those distance what will happen, your center of pressure will tend or will approach your center of gravity point. Okay, but they won't coincide, never. They will never coincide. Center of pressure will always be below your center of gravity point. I hope you get this. Now we will be moving to the next topic. That is, we have already seen here two cases. Third cases we will see is hydrostatic force on inclined plane surface. So let me mention it here first. So third point is hydrostatic force on inclined plane surface. Plane surface. Okay. Okay. So let's consider a free liquid surface first. So let's say that this is your free liquid surface. Okay. And we will consider an surface. Let's say that at an angle theta, we have a surface. Let's draw your surface like this. Okay. So okay, let me make it again. Let's say this is your plate, okay, and I will be making it very thin. Okay. Okay, so let's say that surface is like this. Okay, and this surface, okay. So let's say that this angle is your theta, this angle is theta, and this point is A. Okay, sorry, O. And if I want to project, if I want to project this plane in like top view, so this should be something like this, let's say. Okay, let's say this is your certain surface. I hope you don't go on drawing here. Let me. Okay, so let's say that this is your CG. Let's say that this is your center of gravity. Okay, and I will be making one more line here. Let's say this is your line. Okay, okay. So this point here indicates your CG. Okay, and this distance is your h bar. Okay, and let's at a distance. Okay, and one more thing. Okay, let's first consider your element like at a distance h. Let's consider an element. Okay, and the depth variation, let's say, is your dh. Okay, and one more thing. Let's say that from this point O, if we measure along the plate, so let's say that this y bar is your like depth of CG along the plate. Okay, and let's say that this element here, this element here is at a distance y. Okay, is a distance y and does have your dy distance. Okay, variation. Okay, and let me also like point it out here. Okay, okay, this is your dy, and of course let's say this is your area is dA. Okay, and let's assume one more thing here, that this point here is your CP. Okay, as I mentioned earlier that CP is below CG. Okay, and it will be indicated here in your side view, edge view, or we can say edge view. Okay, and this distance here is, this distance here is HP. Okay, okay, or like here we have considered this as YP, so let's write YP only. Okay, now this view here is your edge view. This is your edge view of the blade. Okay, and this view is your normal view, normal view of the blade. Now if I want to calculate your hydrostatic force acting on this body and your center of pressure distance from the free surface on this body, for that first I should, let's find your relation between your y bar and h bar. Okay, so what I can write here, so let me write. So first, before that, let's write your pressure at this point over pressure over strip dA, pressure over strip dA. Okay, so dA area with strip we have uh, like taken here. So the pressure at that point will be your rho gh. Okay, so rho gh is the pressure at that point. Okay, now elemental force if I talk about, so dF on that area dA will be given by rho gh into dA. Okay, and one more thing, if I like from this uh, let's consider this is a similar triangle here. Okay, so I can write that your y, that sine theta is equal to h by y. So from here I can write h is equal to y sine theta, y sine theta. Okay, so now we will be using this here. So before that, let's first, so let me write here. So rho g times of h we will write as y sine theta, y sine theta times of dA. This is your dF. Okay, now if I want to obtain your value of force, so I can write dF is equal to F is equal to like integration of dF. Okay, and I can write it as rho g sine theta integration of YdA. Again, this YdA is your first moment of area of this elementary area dA. So I can write it as your F is equal to rho g sine theta times of your YdA. I can write it as your y bar times of A, or A times of y bar, A times of y bar. Okay, or let instead of this, let me write something like this. So I can write y sine theta is equal to y by h is equal to y bar by h bar. Okay, so from here I can write y bar is equal to h bar sine theta. Okay, okay, sorry, I written it in opposite. So this is your h by y, perpendicular upon hypotenuse, is equal to h bar upon y bar. Okay, so from here we can write from here. Okay, now here we can replace y bar using your h bar upon sine theta. So if we solve this, so from here we will obtain f is equal to rho g times of y bar I can write h bar upon sine theta. So sine theta and sine theta will cancel out. So this will remain as similar to like this. Here we have written f is equal to rho g ah bar. Here again we have obtained rho g ah bar. Okay. Now if we let me write it in different color so that it will be visible. So f is equal to rho g a h bar. Okay, now if I consider your rho g h bar, so like in this case and also in this case we have obtained this same same cheese. Okay, same thing. Now if I talk about your pressure at cg, so pressure at cg is given by your rho g h bar. Okay, so your force on the inclined plate is always given as pressure at cg times of area of the plate. Okay, so force on cg will be equal to rho g h bar into a, and this is equal to force, hydrostatic force that is acting on your cp also. Okay, I hope you get this point now. Okay, and similarly also in this case also we have like same force value, like your hydrostatic force on the plane surface is independent of orientation of the plate or the surface inside the water. Okay, the force will always be same. Now if we talk about your distance of center of pressure from the surface, so for that as I mentioned earlier, that is okay. And let me mention it before that. So F is equal to pressure at centroid, pressure at centroid into area. Okay, as I mentioned earlier. Okay, now to calculate your center pressure, I have mentioned earlier that you have to calculate the moment of area, moment of the force. Okay, so what I can write, taking moment of force about O, and this point here is your O. About this point we will take here your moment. Okay, so what we will write, we will write your dm, small moment for this elemental area dA will be equal to df into y. Okay, and df value is your, let me write it here, so rho g sine theta times of y square dA. Now this y square dA is your second moment of inertia. Okay, so if you substitute it here, so I will okay, sorry about that. So this there is an integration here, so this is small elemental moment. Okay, Now moment, if we integrate this, so we will obtain it as rho g sine theta times of integration of y square dA. Okay, so I can write my moment of inertia m, or f in df into y. I can write moment of inertia is equal to fp is the, let's say fp, sorry, f is the hydrostatic force here. So f is into, this is, let's say, okay, okay, one more correction let me make here. So let's say that this is hp and yp is your this distance. This distance is your yp. Okay, so from here I can write that df into y is equal to f into yp. This is a moment. Okay, f is a hydrostatic force time, at a distance of yp. Okay, now this will be equal to your rho g sine theta, rho g sine theta times of y square dA. I can write it as I node. Okay, moment of inertia about your free surface. Okay, so from here I can write my yp is equal to rho g sine theta I naught. So if I divide it by f, so f is equal to rho g a h bar. So what will I get? I will get I naught sine theta divided by a h bar. Okay, and if I substitute the value of your y, okay, and one more thing, here this is yp, and if we have to calculate hp, so let me extend one more part here. This is also equal to your hp upon yp. Okay, so if I want to write hp from here, so hp is equal to yp sine theta. So from here I can write hp is equal to yp sine theta. So this will become I node sine square theta divided by h bar. H bar. Okay, and now we can write I node is equal to ig plus ah square. Oh sorry, I node is equal to ig plus ay bar square. Okay, so I node is equal to ig plus a y bar square. Okay, this is I node times of sine square theta divided by a h bar. Now h bar here, h bar we can write it as h bar is equal to y bar sine theta. Okay, so y bar times of sine theta. Okay, so if we solve this, so from here we will obtain my hp is equal to ig upon a, let's write it h bar only. Okay, plus, now here if we solve this, so I will obtain from here y bar. Okay, and I can sorry, y bar times of sine theta here, y bar sine theta, and from here I can say that y bar sine theta is equal to h bar. So this will be h bar, and here I forgot to mention sine square theta plus ig upon h bar times of sine square theta was equal. Okay, so this relation will be very useful in case of your to calculate force, sorry, center of pressure distance from the free surface in case of your inclined surface. Okay, so this is your center of pressure height. I hope you understood till here. Now from here, if like I have to assume your vertical plate, So I can say that my theta is equal to 90 degree. So if I substitute theta is equal to 90 here, theta is equal to 90 here, so sin theta will become 1, and this equation for HP and YP will become same. Okay, and if I say that this is in your horizontal plane, so theta will become 0. So for theta is equal to 0, I will only get y bar. So from here I can also say that your CP will lie here only. Okay, CP and CG both will lie here. Okay, now let's move to your next topic, that is your pressure prism or pressure diagram or prism. If I talk about, so this is your pressure diagram, or you can say pressure prism. Pressure prism. Okay, so if I talk about pressure prism, so pressure prism is basically your graphical representation. It is your graphical representation representation uh, of pressure variation pressure variation over a surface over a surface. Okay, so let's consider a, let's say that this is your free surface line. Okay, and we have some surface here. Let's say this is your surface, and if I, let's say, want to draw your pressure variation here, or not like this, let me draw it like this. So let's say that this is here is your, okay, this here is your surface. Okay, and we have to so in this surface, if I want to draw your pressure variation, so I can say that let's say at this point, let's say first that this distance is a, say the distance is a, and this side is, let's say, b is the, this dimension is b. Okay, so if I want to, let's say, draw the pressure at these points, so here, okay, so this will be your pressure variation on top of the plate. Okay, and if I talk about the variation along this length, so variation along this length can be represented by, like, what we will do, we will the dimension will increase. Okay, so let me increase the dimension gradually. Okay, so let me draw a line first here, and after that I will, okay, so this is your pressure prism here. Okay, like pressure variation on the vertical line. Okay, this is your pressure variation on the horizontal line, on the top line, and similarly parallel to this will be your pressure variation on this the behind edge, and parallel to this will be your pressure variation on this bottom edge. Okay, uh, on, no, sorry, not parallel, like this here from this point to this point will be your variation on this point. Okay, and if I draw a dotted line, let me draw it here first. So this line will be corresponding to this corner. Okay, okay. So this prism here, this will like include the prism here. Okay, so this here is your pressure prism. Okay, this here is your pressure prism. Okay, sorry. This here is your, sorry, pressure prism. Pressure prism. Now, what is the benefit of making the pressure prism? Okay, like you have to basically calculate hydrostatic force F, okay, and your center of pressure point. Okay, so from this pressure prism you can calculate both the value directly. How? So pressure prism, the your force is basically the volume of pressure prism. So if you know the volume of pressure prism, so you can calculate your hydrostatic force. And to calculate Cg, this is your uh, like Cp is your Cg, your center of gravity of prism is your center of pressure. Okay, I hope you understood this point here from here. Okay, so these 2 points are the important one here. So force F is the volume of pressure prism and Cp is the Cg of pressure prism. This pressure here is P top is equal to rho g times of A, and pressure at bottom here P at bottom is equal to rho g times of A plus B. Okay, I hope you get this point. Okay, what is the benefit of pressure prism? So you can like draw this pressure prism in case of your inclined, vertical or horizontal, all type of surfaces. Okay, but this pressure prism concept you can generally use. We generally use in case when your figure is, let's say, rectangular. Okay, because in case of your circular, if I let's say see here circular plate, so in case of circular like prism over circular base, so what will happen, to calculate calculation of volume will become difficult. Okay, so in these cases we generally ignore, like don't use your pressure prism concept in case of your circular or triangular. Okay, triangular basis also we don't use. We generally use your pressure prism concept in case of your rectangular base only, because in that case your calculation of volume becomes easy, because it is basically the area of trapezium on this face, area of trapezium, this is a trapezium. Okay, so area of this trapezium times of your this dimension is your volume of the prism. Okay, now before moving to next topic, let's first talk about your different surfaces and their area, center of gravity, their moment of inertia about your center of gravity, and your HP, that is your center pressure height from the free surface only. Okay, now your center of gravity of this uh, rectangle surface rectangular surface center of gravity, but if we talk about area, so area will be B times of H. Okay, center of gravity, that is H bar, will be your H by 2. Okay, Ig will be your BH cube by 12, BH cube by 12, And your Cp, if we talk about, so Cp will be 2h by 3, 2h by 3, 2h by 3. Okay, because your pressure variation will be in terms of triangle, and triangle, your centroid of the triangle is at distance 2h by 3 from the top. Okay, if we talk about your trapezium, then area of trapezium is your half into base plus length, like sum of two opposite sides, sum of two parallel sides. Sum of two parallel sides is a plus b times of h. Okay, so this is your area. Okay, so after area, this is time of h bar cg. So cg of your trapezium lies at a distance of, like, if you're talking about from the top, if you're talking about from the top, then top side, top length plus twice of bottom length, okay, upon a plus b into h by 3. This is your cg. If I talk about your like ig, so ig for this trapezium is given by a square plus b square plus 4ab divided by 36 times of a plus b. Okay, and this overall times of h cube. This is your ig. Okay, and if I talk about cp, then cp is at a height of a plus 3b, a plus 3b upon a plus 2b, okay, times of h by 2, h by 2. Okay, this is the height of cp. Okay, now if I talk about your triangle with the apex at the top, so your cg, sorry, if your area will be half into b times of h, your cg, here cg will be here, okay, here cg will be, okay, and cg will be at 2h by 3, 2h by 3. I about cg will be bh cube by 36, bh cube by 36, and your depth, like center pressure height will be 3h by 4, 3h by 4. Okay, if I talk about with base at the like free surface, so area will again be same, half into bh. Your center of gravity will be at h by 3. This is your cg. Okay, your moment of inertia about center of gravity will be again same, bh cube by 36. Okay, but what will vary is your center pressure depth. Okay, and center of pressure will be at h by 2, h by 2, h by 2. Okay, h by 2. Now in case of circle, if we talk about, so cg is at your center of the circle, center of circle is cg, and first area is your pi by 4 d square. Your cg is at d by 2 distance. Your I is pi d की power 4 upon 64. Okay, ig, and your cp, if we talk about, so the cp is 5d by 8. Okay, and for in case of semicircles, your like area will be pi by 8 d square, half of circle area. Okay, this height your will be your, like if I talk about, let's say, is equal to diameter is equal to 2r, so this Cg will be 4r upon 3 pi. Here Cg, okay, so 4r upon 3 pi uh, is your distance to Cg. If I talk about moment of inertia about G, so this that will be pi minus 8 pi by 8 minus 8 by 9 pi times of d की power 4 by 16, okay. And if I talk about center of pressure, then that will be at 3 pi d upon 32, okay. So these are a few important relations that will be useful in our study, okay. Okay, I hope you will get this. Now we will be moving to our next topic, and next topic is your like hydrostatic forces on curved surfaces, okay. hydrostatic hydrostatic forces on curved surfaces, on curved surfaces, okay. So for hydrostatic forces on the curved surfaces, we will first consider an example. So let's consider a surface. Let me draw it here. So let's say there are two supports. This is a vertical support, and this is a, let's say, a curved surface. Let's say for this curved surface, if we take at a distance, let's say h from the free surface, we take an element. Let's say this is your element, this is the dA, okay. So a hydrostatic force acting on this small surface df df will be some value, let's say rho gh, okay. And as your h value varies, as your h varies, your force magnitude and force direction will also change, okay. So to overcome this, what we do, we resolve this hydrostatic force F acting on the surface in two parts, with horizontal component force and vertical component force. So let me, okay. So from here we obtain horizontal component of force, and second point is vertical component of force. Okay, on on surface, or okay, on curved surface you are talking about. Okay, now if I talk about your magnitude of this, first let's like calculate these values. Okay, so if I talk about your elemental force df acting on this small surface, that will be equal to your rho gh times of dk. Okay, so if I want to, let's say, calculate the hydrostatic force, so I will write it in terms of your integration of pda. Your area varies, and your okay, but before that, your pressure varies with h, and your area varies. And how does your area varies? Because this area is generally like taken, like if you take a normal surface, so like your normal to your surface, normal to your area is continuously varying. Okay, I hope you get this point. Okay, so what we do, like this component df which we have considered. So let's say this is area is your da, let's say this is your area da. Okay, so what we do, we have made into two parts. Let's say this angle is, let's say this angle is theta. Okay, okay, so this area is your da sine theta, and this area is da cos theta. Okay, and if we talk about the forces, then p pressure is acting on this, or my like df is acting on this. Okay, so we can say that or let me draw it like this, like actual force, your df is acting like this is your df. Okay, and we can make it into two components, let's say this one and this one, where your this angle is theta. Okay, and this df value is like your p times of da, and your horizontal component dfh is equal to df cos theta, and your vertical component, that is dfv, is equal to df times of sin theta. Okay, I hope you are clear up to this point. So if I talk about your horizontal force, so I can write that dfh is equal to df cos theta, as I written here. So I can write your df is equal to rho g uh, rho gh times of da cos theta. Okay, and from here I can write it is equal to, or I can integrate it to uh, obtain your. Okay, and one more thing, I can like write da cos theta as your dh, let's say dh, and this da sin theta is da. Okay, like I mentioned here h, because like this dfh will be acting on this da cos theta area. Okay, on this component of area in horizontal area for horizontal force. Okay, so we can write it as rho g h times of your dh. Okay, and if I want to calculate, let's say, horizontal force, I will directly integrate this term, and we will obtain it, this as rho g times of integration of h times of dh. Okay, and this h dh is your first moment of area, so I can write it as your fh is equal to rho g a h bar. Rho g, sorry, this is your a h, this is your horizontal projected area. This is your horizontal component of the force, where your ah is your projected area. Projected area, and this projected area is on vertical plane, on vertical plane. Okay, similarly we can also calculate your vertical force, that is dfv is equal to df sine theta, and this value will be equal to rho g h times of dA sine theta. Okay, and can be written as rho gh times of, now this dA sine theta can be written as your dav. Okay, dav. Okay, now if we integrate this, so I will obtain fv is equal to integration of dfv is equal to rho g times of integration of h into dav. Okay, now h into dav, if I talk about h into dav, so this small element, okay, times of height will be your small volume, can be written as rho g times of dv. Okay, and for integration of dv. Okay, so I can write my vertical force is equal to your rho g v. Okay, where your v volume, v is the volume, v is the volume of liquid above curved surface, curved surface, and of course up to free surface, up to free surface. Okay, so you have calculated both fh and fv. So if I want to write your horizontal and vertical component force, if I want to write your horizontal and vertical component force, so how will I write it? So horizontal component of force is equal to your hydrostatic force, hydrostatic force on vertical, on vertical projected area, projected area of curved surface, curved surface, and this force will act on, and will act on cp, act on cp of corresponding area, corresponding area. Okay, and similarly your vertical component of force we can define as it is your weight of the liquid or weight of the fluid, weight of the fluid contained by curved surface, curved surface up to free surface, up to free surface, okay, and acts at CG, okay, of the corresponding weight, okay. So from here, since I have obtained both FH and FB values, so I can write that my force F, my force F is equal to resultant of both horizontal and vertical components, FH square plus FV square, okay. So this is it, okay. Okay, so with this we have completed our theory on these hydrostatic forces on the surfaces, and now in the next session we will look into our questions. Thank you.